Hello, everyone, and welcome to our ACM 2025 presentation. This work introduces our paper titled RA Touch Retrieval-Augmented Touch Understanding with Enriched Visual Data. To begin, let's define the core concept of our work, visuo-tactile perception. Visuo-tactile perception aims to replicate the human-like ability to perceive an object's properties, such as texture, hardness, and shape, by integrating information from both seeing and touching. This capability is crucial for enabling advanced physical interaction in fields like robotics and assistive technology, particularly in complex tasks that involve deformable or occluded objects. Vision and touch work in a complementary manner. Vision provides global information like an object's overall shape and appearance, but it's insufficient for perceiving physical properties like texture. This is where touch becomes critical, providing local surface details through direct contact and compensating for the limitations of vision. Together, these two modalities enable a richer and more robust understanding of physical materials, which is the foundational principle for our work. However, visuo-tactile perception faces a significant challenge. While progress in fields like vision and language is driven by large-scale datasets, this is difficult to replicate for touch. The process of collecting tactile data is inherently costly and complex, creating what we call the tactile bottleneck. This leads to a severe scarcity of data, which is a major obstacle for the field. Addressing this data scarcity is the primary motivation for our research. To address this, our core idea is to learn touch from vision language. This is based on a key observation: visually distinct objects can often share similar tactile properties if they are made from similar materials. For example, a leather sofa and a leather jacket, while different, share tactile qualities like being smooth and firm. This implies that we can infer an object's feel by leveraging material cues from abundant visual data, even without direct tactile supervision. This insight is the foundation of our method, offering a path to bypass the tactile data bottleneck. Based on this core idea, we propose our novel framework, RA Touch. RA Touch is a retrieval-augmented framework that leverages external visual knowledge to enrich tactile perception. As illustrated in the architecture, our tactile-guided retriever first generates a query from the inputs to search our knowledge base, ImageNet-T, for relevant samples. These samples are then processed by a texture-aware integrator, which selectively filters for the most relevant textural cues. Finally, this augmented representation is fed into a large language model to generate a descriptive output, enriching tactile perception without requiring new data collection. Our retrieval approach requires a knowledge base, but conventional visual datasets lack tactile semantics. To solve this, we constructed ImageNet-T by recaptioning a large visual dataset with descriptions focused specifically on tactile properties. For each image, we generated 5 adjectives describing only how it feels to the touch. This process transformed a standard visual dataset into a rich, tactile-aware knowledge source, which is foundational to our framework. Now for our first key component, the tactile-guided retriever, which generates an effective query for retrieval. A simple query using only image or tactile features is insufficient, as one can miss texture details while the other lacks global context. To solve this, our retriever constructs a joint query. It applies cross-attention, using the tactile feature as a query to selectively extract relevant textural details from the visual feature. This process creates a powerful, semantically aligned query, enabling a much more precise retrieval. The generated query then searches our ImageNet-T knowledge base using cosine similarity, retrieving the top K most semantically similar vision language pairs. Crucially, this allows our method to find visually different but tactily similar objects. For example, for a leather sofa, the retriever successfully finds samples like leather gloves and shoes. These retrieved samples provide rich, tactilely relevant context for the final integration step. Finally, our second key component, the texture-aware integrator, effectively integrates this external knowledge. Retrieved data can contain irrelevant noise, so simple fusion is suboptimal. To address this, our integrator uses a cross-attention mechanism, where the original tactile input acts as a query to selectively extract only texture-relevant information from the retrieved samples. This process provides a clean, texture-focused representation to the language model, ensuring a more accurate and nuanced final output. Now we present our quantitative results on the TVL benchmark. As the table shows, our proposed method, RA-Touch, consistently and significantly outperforms all baselines, including the fine-tuned TVL Llama model. Notably, our strongest model achieves a score of 5.36 on the TVL benchmark, demonstrating a substantial improvement and confirming the effectiveness of our retrieval-augmented approach. Our qualitative results further highlight our model's capabilities. For the first sample, the wooden surface, and the second, the bumpy matte surface, our method consistently retrieves more tactily similar samples than approaches that use only a single modality. This ability to retrieve semantically relevant samples is key to why RA-Touch generates a more descriptively accurate final output, highlighting the real-world effectiveness of our framework. To validate our components, we conducted an ablation study. The results clearly indicate that adding each module, the tactile-guided retriever and the textural-aware integrator, progressively improves performance over the baseline. For instance, with the VIT-based backbone, the full RA-Touch framework boosts the TVL score from 5.03 to 5.32. This systematic improvement confirms that both modules provide complementary benefits, validating our architectural design. We conducted further ablation studies to analyze key design choices within our framework. First, the top table compares retrieval strategies. It shows that our proposed tactile-guided query consistently achieves the best performance, validating our approach of constructing a joint query. Second, the bottom table investigates the impact of caption type. The results show a clear trend performance improves with semantic richness, and the most substantial gain is achieved with our tactile-focused descriptions from ImageNet-T, highlighting the importance of a tactile-aware knowledge source. In conclusion, this work introduced RA-Touch, a novel retrieval-augmented framework that enhances tactile understanding by leveraging abundant visual language data. This approach, based on our core insight that different objects can share tactile properties, allows us to shift away from costly and labor-intensive data collection. Our results demonstrate that RA-Touch is a scalable and data-efficient solution, opening new directions for multimodal grounding in other low-resource sensory domains. This is our project page. If you have any questions, you can contact us by email. Thank you for your attention.